Hi everyone. So this is a lecture series on advanced structural analysis. The first topic in this series is the slope deflection method applied to the analysis of beams. This is Dr. L. Venkat, Professor of Civil Engineering, Gayatri Vidya Parishad College of Engineering Autonomous. So let us see how this a continuous beam can be analyzed using a slope deflection method. So if you see what is a slope deflection method, that means when you apply a rotation, right? So this beam will try to deflect like this, and when you draw a tangent here, this is a slope theta. Let us say this support is A, this support is B, this is theta B. Since support A is fixed, there is no slope at A. So how much is the movement produced at A due to rotation theta B at B support is 4 EI theta B by L if the span is L. And because the far end is fixed, the movement produced at A is half of the movement generated at B. This is 2 EI theta B by L. Now if the support A is hinge and support B is fixed, let us say, if this is a condition, this is general condition, and if you apply a unit rotation or a rotation of theta, rotation of theta here at support A, if I draw a tangent here, so this rotation is theta A if support A support B, the movement produced is 4 EI theta A by L, and the movement transferred at support B is 2 EI theta A by L. Then suppose the one of the support is settles. If this is a beam, actual beam, and because of some issues at the support, if this right hand support is deflect by amount of delta, then the movement produced here on this beam, since both ends being fixed, because of support settlement at B is minus 6 EI delta by L square, the span is L everywhere, and this is minus 6 EI delta by L square. Now adding the total moments at A, adding all these two moments at A and all moments at B independently. So the movement produced at A, B, span AB at A is nothing but here, which is 2 EI theta B by L plus 4 EI theta A by L minus 6 EI delta by L square. If you write taking common of 2 EI by L, so what we get here is 2 theta A plus theta B minus 3 delta by L. So this moment is produced at an A of span AB, and this is only because of rotations and displacement, that is sinking support at B. If there is any external load on the beam, so this produces a fixed end moment on the joint. So then the final moment at AB is equal to MFAB plus 2EI by L 2 theta A plus theta B minus 3 delta by L. So this is the slope deflection equation. Slope deflection equation. So depending upon this end condition, the theta A, theta B can be 0 or maybe existing. And delta, if support sinking is there, delta value will be there. If delta support sinking not there, delta will be 0. If the right hand support is upper compared to the left hand support, then this minus 3 delta by L will be plus 3 delta by L. Right? So this is a slope deflection equation used for analyzing a continuous beam. So let us see an example of a continuous beam for the movements. So let us see a continuous beam which is A, B, C and D, and we need to analyze this beam using slope deflection method, and we have to draw a bending moment diagram. Now first we need to find out the fixed end moments on the beam. So let us find the fixed end moment MFAB. That means a fixed end moment at AB. And AB span being a UDL load, that means every span is taken as a fixed beam. Every span is taken as a fixed beam. That means the beam is something like this, a span AB. And for a UDL load of 20 kilonewton per meter, so what is friction moment produced here, which is minus WL square by 12, and this produce a clockwise moment of WL square by 12, right? So that is the friction moment here. So MFAB is minus WL square. W is your 20 into 6 square by 12. So this is equal to minus 60 kilonewton meter, and MF BA will be a positive WL square by 12. So 20 into 6 square by 12, which is 60 kilonewton meter. And let us have next span, which is MF, friction moment, for a span BC, which is point load in the middle, WL by 8. MF BC, which is a negative, minus 80 into L is a 4 meter by 8, which is your minus 40 kilonewton meter. And MF CB, which is plus, that means 80 into 4 by 8, which is 40 kilonewton meter. This is as far as friction moment concerned. Now let us look at a slope deflection equation for a span AB. Right? So MAB is equal to MFAB plus 2EI by L, 2 theta A plus theta B minus 3 delta by L is in general. Now we know that MFAB is minus 60 kilonewton meter plus 2E, and the moment of inertia for the span AB is 2I by length of the span AB is a 6 into 2 theta A. This support A being a fixed support, theta is 0, so this is 0, plus theta B, this is a rotation, will exist at B, so theta B is unknown, and support B is not sinking, not mentioned in the question, that means this is 0. 3 into 0 by some L. So this is everything 0. So this equation will be minus 60 plus 2 by 3 EI theta B. So this is MAB. Let us have 1. This is MAB. Moment at A in the span AB. Now similarly, let us work out the movement at B in the span AB, which is MFBA plus 2EI by L, 2 theta B plus theta A minus 3 delta by L. So this gives me, if you look at it carefully, this theta A is 0 and delta is 0. I left with only 2 theta B. So I is 2I, L is a 6 meter, MFBA my 60 kilonewton meter. So just substituting this, MBA is 60 plus 2 into E into 2I by 6 into 2 theta B. So this is 60 plus 4 EI by 3 theta B. So this is, let us say, second. So now let us go into the next span, M BC. So span BC, we know span BC, there is a rotation at B and there is a rotation at C. Both the joint have a rotation. So therefore, MFBC plus 2EI by L into 2 theta B. The first quantity here, twice the rotation, plus theta C minus 3 delta by L. So we know this delta is 0. So MFBC is minus 40 plus 2, and the moment of inertia for the span BC is I only, 2EI by L, length is the 4 meter into 2 theta B plus theta C. So this is a half. This is MBC. This means this is a half. So let us say this is equation 3. And let us write MCB, the same equation, MFCB, which is 40 plus 2EI by L is a 4 into 2 theta C plus theta B minus 3 delta, which is 0. So I will not write. So this again half. So this is the equation 4. Okay, CB. Now carefully look at here what happens. These are the basic slope deflection equation we have written here. Now we have unknowns. The unknowns are theta B and theta C. So we must have two conditions to solve these unknowns. So look at carefully the beam here. At joint B there is an equilibrium, and at joint C also we can take an equilibrium. So joint B means MBA plus MBC is 0. Then MCB plus MCD must be equal to 0. Okay. So now using that means MBA plus MBC is equal to 0. This is 1. And MCB plus MCD is equal to 0. So these are the two joint equilibrium equations. Joint equilibrium equations available. So let us solve this to get a theta B and theta C. So let us have MBA plus MBC is equal to 0. That means MBA, if you carefully see MBA here, MBA 60 plus 4 EI by 3 into theta B, MBC minus 40 plus EI by 2 into 2 theta B plus theta C. So this writing here 60 plus 4 by 3 EI theta B and MBC minus 40 plus EI theta B plus half of that means 0.5 times EI theta C is equal to 0. Now we can see 4 by 3 theta B and EI theta B, right? So this will give you 2.33 EI theta B. So 2.33 EI theta B plus 0.5 EI theta C and 60 minus 40 20, so that other side will be your minus 20. This could be one of the equation. Now the summation of moment at C, which is MCB plus MCD, is equal to 0. The MCB we already have here, MCB here, 40 plus EA theta C plus half of EA theta B. 40 plus 0.5 EI theta B theta B plus EI theta C. Then MCD, if you look at the beam, what is MCD here? So 40 into the distance, 40 into 2, which is 80, which is clockwise movement here, right? So clockwise movement, which is 40 at this side, right? So this beam will have a resistance movement of anti-clockwise of minus 80. So MCD is minus 80. So minus 80 is equal to 0. So here, so 0.5 EI theta B plus EI theta C, this is minus 40, the other side is your 40. This is, let us say, equation 5 and this is equation 6. Solving these two equations for theta B and theta C, just like here, multiplying with the 0.5, by multiplying the equation 6 with the 0.5 and subtracting that, so what do you get? 0.25, 2.33 into minus 0.25, and this theta C get cancelled out. This will be minus 20 minus 20 is a minus 40. So what we get here is a theta B. So EI theta B is equal to 19.2. And in fact 2. That means theta B is 19.2 by EI. And substituting back into one of the equation 5 or 6, so EI theta C is equal to 49.6. So that means this implies theta B is nothing but by 19.2 by EI, and theta C is nothing but my 49.6 by EI. By substituting this theta B, theta C in the final equations, what we got it here, theta MBA 60 plus 4 EI by 3 theta B already obtained, or EI theta B already obtained. So using that, so I can find out MAB is equal to minus 60 plus 2 by 3 into minus 19.2. So here EI theta B equal to minus 19.2, which means theta B is minus 19.2 by EI, that correction. So then MAB is minus 60 plus 2 by 3 minus 19.2 by EI get cancelled out. So this gives me of minus 72.8 kilonewton meter, and MVA gives me 60 plus 4 by 3 minus 19.2, which is 34.4 kilonewton meter, and MBC has to be minus 34.4 because which is minus 40 plus minus 19.2 plus 0.5 times 49.6 will give you minus 34.4 kilonewton meter, and MCB will be equal to 80 kilonewton meter. So this is what the moments obtained. So we can draw the Venn diagram of this beam. So let us take the beam. So this is a support A, and this is support B, and this is support C, and here is the load. Okay. Now, so if you see the, I will draw here the simply supported Venn diagram because of UDL load. Let us say this is parabola. Okay, and this is your here. So WL square by 8. This value is WL square by 8. So this is WL by 4. And due to this, we'll have a negative moment. These are the due to external load. So now what are end moments here? MAB. So I will draw the color here. Here. So MAB minus 72. That means this is the moment minus 72. At B, how much it is? 34. 34. So almost half of this. So when you join this, and at the C is 80, so this 80 has to balance, so it is meet here. So this is 72.8, this is 34.4, this is 80. Now depending upon the value of WL square by 8, this may be little higher. So this could be something like this also. So now the effective moment diagram will be this. This is moment, effective moment is this. Depending upon the value of WL by 4, so it may go up or down. So this is the moment when BMD for the continuous beam. Okay, thank you.